a compressor fail, okay? And if they were in order to the worst to the least, the worst would be overheating by far, okay? And I'll talk about that along the way, but that is the number one killer of compressors. And most of the reasons why compressor fails, ironically, and this is always kind of a slippery slope for me, especially now that I work for Emerson, is it's 9.9 times out of 10, it's a system issue and not a compressor failure. But we do have compressor failures, don't get me wrong, but very, very slim to none. All right. So we're going to go over all these and what they mean to you. And we're going to talk about the compressor checkpoint review, troubleshooting system checklist review, and those kind of things. So, what's our learning objective today? After completing this session, you'll be able to identify the common causes of compressor failures, including refrigerant floodback, flooded starts, slugging, overheating, loss of oil, and debris and contamination. Now, just briefly, I'm going to talk about these two because sometimes, from a new technician's point of view, they see that word flood and they have so much coming at them that they're trying to absorb and learn, they get the two confused. So here's how I teach it. Refrigerant floodback, the thing we need to remember is the system is running. It's refrigerant getting back to our, for lack of better terms, our vapor pump, okay? And anytime that happens, obviously we hear those crunchy noises. Our vapor pump turns into a hydraulic pump and things start to break. When I hear flood back, again, the system is running. With my experience, I immediately think of the refrigerant's not boiling off for some reason, whether that's a bad metering device, out of control, sized wrong, poor airflow across the evaporator, whatever that looks like, okay? But for whatever reason, liquid refrigerant's getting back to the compressor. I feel strongly, I immediately think the refrigerant's not boiling off. It's not vaporizing somehow or some way in the evaporator. Flooded starts, even though there's the word flood again, totally different. And what I mean by that is the system is not running. It's defined as off-cycle migration. Okay, so what happens is it could off-cycle migration could happen in 3 hours, or it could happen in 3 months. So it can be seasonal, or it can be just the difference from the delta T from the condenser to the evaporator. That vapor refrigerant in the evaporator is warmer, let's say, than the condenser oil that by the law of, the second law of thermodynamics, hot wanting to go to cold, that vapor refrigerant finds its way out through the refrigerant lines, gets into the compressor, which is cooler, and absorbs in the oil and condenses, raising that, oil refrigerant up, diluting it, okay? And that causes catastrophic damage. And we'll talk more about that. Slugging simply can happen with refrigerant floodback or flooded starts. Slugging to me is like saying it's a bullet. You've taken a liquid slug to the compressor and parts start to break. Now, some people, like our competitors, will define it as, well, slugging happens when a big, unlike floodback, it's like one glob of refrigerant coming back to the compressor. And that's true. Okay. But the moral of the story is slugging is liquid refrigerant coming back. When it's a refrigerant cooled compressor, okay, it's going to happen typically on flooded starts. On a air cooled compressor, slugging's typically going to happen on liquid floodback. And I'll talk more about that. Overheating, kind of self-explanatory. Loss of oil, pretty much self-explanatory. And debris and contamination, just one little fun fact here is this is the biggest piece of the pie that's growing. Now, it's far from overheating. Again, that's the number one reason. But debris and contamination is the number one growing piece of the pie when we talk about failures. All right. And this is just a theory of mine, being an older guy and being in the field quite a few years, over 25 years, is this. What I found since I've been at Emerson, the short 4 years I've been here, is what falls into the category of contamination or debris, or I should say debris, we've added contamination after the fact, is your dyes, your sealants, all these special new devices and components that they sell now at your wholesalers that weren't there before years ago. So, you'd be surprised how many compressors we take apart in our teardowns. I mean, as many as 8 compressors out of 10 will have dye in them. And you and I both know we're altering that our PT charts, basically. I mean, that's what our PT charts are made of. It's the saturation temperature, and saturation is defined as liquid and vapor of the refrigerant mixed together, whatever that looks like, whether it's multiple components or a single component. But when we start adding dye to it, especially people that add dye over and over, each technician comes out and says, "Oh, I'm low on refrigerant. I must have a leak. Let me put some dye in it and then charge it up and get on my way." Well, if people keep doing that, I've got pictures, and I think I'm going to show you some of them at the end of the class, where literally the refrigerant oil looks like radiator fluid. And I'm not joking. And we see it all the time. It's a lot of them you don't have to look very hard. Some of them I have to get my UV light out, my dye flashlight, and stick it in the compressor just to show the students there is a trace of it there. It's not as visible as this one, but it's there. Okay. So that's what we're going to talk about. Recognize compressor damage and wear patterns to determine the cause of failures, and describe strategies of preventing common system issues that lead compressor failure. What this pie chart's telling you is, notice we have field diagnosis over here and the actual root cause. So this little piece of pie here, this piece of pie or this pie chart, is what you and I, or I should say I and other technicians, see in the field if you tear compressors down. We diagnose compressors for being majority electrical problems. Why? Because a lot of folks, like myself included, don't tear compressors apart to find out the real culprit of the root of the cause of the problem. We take our voltmeters out, we test the compressor, we say, it's shorted to ground, it's open, whatever. We tag it, bag it, send it back to the wholesaler as electrical issue, and whatever we write down. Nine times out of 10, that's what we do. There is a small piece of the pie that we say it's mechanical. Okay, there was an electrical issue, there was mechanical. Okay, when we tear the compressor down at the factories in our teardown area, and some of these folks have as much as, I think Mike's been here 42 years, believe it or not. I think he's getting ready to retire. But these folks our Emerson employees that work in this area, they've done this so long out of repetitiveness. They can tear a compressor down, whether it's welded or semi-hermetic, and they can tell you within minutes, like within a half hour, they can lay the pieces of the puzzle out, almost like a crime scene, and it's like a fingerprint to them. Because you and I both know, or at least I know, maybe you don't know, the way the compressors are manufactured and made today, a lot of that tooling hasn't changed for 40 years. Some of our semi-hermetic, for examples, they don't change. It's still the same way it was designed 40 years ago. And really, some of the same things could be said about the scroll. What changes is modulation, or modules that go on it, like core sense and different things like that. Different ways it's wired, whether it's a solenoid valve or whatever. But the actual compression, the way that the strategy they do that, the engineering behind that, really has not changed a lot since 1986 on the scrolls. It really hasn't. Not a lot's been tweaked there. The reason I'm telling you that is the markings are the same. So when we get liquid flood back, those markings have been that way since day one. They can tell when something's gotten too hot, the way it's colored, the way it's scarred, the way it smells, whatever. They can lay those things out and say, if you do this every day, you get pretty good at it. And in our class, for example, when we walk these students that's never been to a teardown class, these technicians, whether they've had 25 years or 25 days in the industry, they have a pretty good grasp, believe it or not, in groups of 3, of telling us as we go around the room and listen to their story, hey, I'm dealing with an air-cooled compressor, and this is what we think happened. And quite often, they're spot on because of the 2 days prior to the training, like you're seeing now, of what's going on. A little more in depth, obviously, but still, this is a piece of what we do. This is just saying field analysis pays dividends. Don't keep putting compressors in Because again, look for the cause. What happened? Why did it happen? Are we fixing the problem, or are we just changing compressors out? Okay, because nobody wins in warranties, right? Nobody wins in warranties. We refer to this as the ABU model. It's all broke up. But all joking aside, this is a refrigerant cooled compressor that obviously took a major slug this would be a flooded start. Notice the scarring right here on this bearing, where this bearing was on the shaft. So here are our 6 main reasons that fall under the umbrella: refrigerant floodback, units running, flooded start, off-cycle migration, slug, liquid slug, overheating, we're getting too hot for whatever reason, loss of oil, where did it go, and debris contamination. Okay, whether that's copper shaving or some kind of contamination from overheating or acid of some sort, and how are we going to handle that? So again, this is not going to be in any particular order as far as most common to least common. And again, if it was, this is going to get somewhat redundant because I really like hitting this home to when I'm talking to especially younger technicians. Overheating is the number one. And I'll let a little bit of information out early. Overheating is the main reason for overheating is what we call compression ratio, which simply means your head pressure is too high or your suction pressure is too low or the combination of both. The further that ratio gets apart, the harder that compressor is running, and the hotter that compressor is getting, the thinner the oil is becoming. We're getting a higher viscosity, or actually a lower viscosity. It's getting thinner, so it's getting thin. And in a reciprocal, the thinnest film of oil in a reciprocating compressor is that thin film of oil between the piston and the cylinder wall. Okay, so that starts to cause ring wear, friction, and so on and so forth, which just compounds the problem of overheating. All right, so let's start with refrigerant floodback. Defined as liquid refrigerant returning to the compressor during the running cycle. That's key. Probably should have highlighted that for future classes. Running, it's running. We see the word flood, but flood back is the unit is running. I connect that is something's not boiling off. The refrigerant's not boiling off. Why is it not boiling off? Anytime the metering device has lost control of the liquid refrigerant being fed into the evaporator, more frequently caused by poor airflow across the evaporator. Can't emphasize that enough. If you've ever worked in the field, if you've ever been on a job site, if you've ever known anybody to work in the field, ask them how many times do you run a call and the culprit was the airflow that caused a chain of events to happen. I can assure you, I would go as far as 6 to 7 times out of 10 service calls possibly were connected originally to airflow. I'm not even joking. You'd be surprised. Some young technicians will go out and look for the hardest thing and make it way more complicated. But the first thing you should need to check out is after you activate your, whatever's controlling the system is, what does my airflow look like? Am I getting good airflow? If there's a filter involved, is that clean? Okay. Did someone push stock up against my evaporator? Is it Thanksgiving and we've got a sale on turkeys and they're all domed over the coffin case above that line in the back that says, oh, by the way, don't stack product above this line. There's a reason for that, right? Whenever the load is lost or the liquid refrigerant cannot boil off, one of my favorites right there, that is an indicator of liquid floodback. Now, it's going to look different on different compressors. For example, on an air-cooled compressor, which simply means we're not coming across the bell end or the motor end of the refrigerant, we're coming directly in the head, and it's cooled by either by air, but you can also have a KW, not a K body, but a KA is for air, but a KW designed the same way and have a copper water line wrapped around the belly band. But let's stay with the air cooled. Why would it be different on air cooled? Well, it's coming right in the head. The suction line is connected right into the head as opposed to coming on the opposite end across the motor to cool the compressor. The light blue is simulating vapor. The dark blue is the liquid refrigerant that didn't get boiled off. Discharge gas. Again, here's that thinnest film of oil in this design. Cylinder wall and the piston. What's going to happen? Well, liquid refrigerant, as you may know, is a very good solvent, especially POE liquid refrigerant. It will wash oil away quickly. It is a very good solvent. If you're familiar with a product called RX11, which a lot of contractors use to flush systems on changeouts, which we don't recommend, by the way, this is better than RX11. POE oil refrigerant will just wash it away. This is a cast iron piston. These are oil grooves. The reason I'm pointing that out is we also have aluminum pistons, and it varies depending on the application. Obviously, you have expansion there, so we use cast iron in some cases. But this is an oil groove, okay? But more importantly, what I want to tell you is these cast iron pistons are coated with what we call lubrite, and that lubrite color is black, okay? Notice there's no darkness here, but there is here. This is that POE oil, the solvent actually washing away the lubrite as it goes up and down in that cylinder wall, okay? So that's causing some serious friction. And that's the purpose for this coating on the lubrite, to keep some of that heat down and protect that piston, okay? That's what some of the damage a person would see if they had time, or they made themselves knowledgeable enough to tear the compressor down. And oh, by the way, if you don't know this, I'll get this out of the gate right away. We have a 1-year warranty at Copeland. The OEM will have maybe a 10-year warranty on compressors, as you may know. It's very common for a 10-year warranty on compressors through the OEM. But Copeland, no questions asked, has a 1-year, okay, on top of what anyone else has. The reason I'm telling you that is, in that 1-year period, any compressor of ours, you can ask to have a compressor analysis done. So anyone that has a compressor failure in the first year, a Copeland compressor, can request a compressor analysis. And that's what we do at our teardowns. So how does that work? You take it back to the wholesaler. You say, hey, I need a new compressor, but I want this one, a compressor analysis done. It's still in the first year warranty. I want to know why this compressor failed so I can prevent the next compressor, hopefully, from failing. Or was it a bad compressor? And they'll send that into us through the teardown area, and they'll get a printout of what actually happened, spelled out to them, that they will issue to you. Now, in certain times of the year, that's not a real quick turnaround. I'm not going to mislead you. You know, in the peak of the season, like in July, that might take 6 weeks, but it's there. Also, a little known fact, you can get a teardown analysis anytime, in warranty or out of warranty. The difference is there will be a small fee through the wholesaler. We don't get into the monies of things, but through the wholesaler. And I think from what I've heard through the years I've been here, anywhere from maybe 50 to $100. But it's well worth it if you're talking about a compressor that costs $7,000 to the
Hey,
contractor.
Don, it's 150, just FYI.
Okay. Is that a standard price all the way across the board, Evangeline?
Yeah, to my knowledge, yeah, it's the only
Okay.
price I've ever heard
Okay.
of or charged.
Very good. Okay.
And
There you have.
that's through us. Wholesaler, I don't know, but if they return it, if you guys call us and ask us for a tear down out of warranty, we will, but it's $150 charge.
Perfect.
And actually, we don't make any money off that. We lose money because of the time, but it just kind of offsets and defrays a bit.
Yeah. 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 No, hey, that's good information. I appreciate it. I'll note that down and share with the other instructors there. That's straight across the board, $150. So again, it's a lot cheaper than a $7,000 compressor, and makes you look a lot smarter at the end of the day, and possibly prevents losing an account. That's what I always share with the contractors. So, but you can get it done outside of the warranty also, but be aware of that. Now, on a refrigerant cooled compressor, that's going to look differently. That marking on liquid flood back. Here again, we're simulating liquid refrigerant. Liquid refrigerant or the POE oil liquid refrigerant. It's going to be heavier than the oil. The oil here is simulated in yellow. This is going to fall to the bottom. We have a pickup tube that you can't see. This compressor's running. Again, liquid flood back, the compressor's running. This pickup tube goes all the way to the bottom. It's not animated here, but it's all, trust me, it's all the way to the bottom. Okay. And that picks that oil up, and there's a hole in the shaft, and it goes down through the shaft and lubricates everything along the way. All these bearings, there's holes drilled in this shaft all along the way. So what's that going to look like? We saw what the air cooled compressor was going to look like, but what's that going to look like? It's going to look like this. We refer to this as progressive wear. Now, this is really cool to start looking at this stuff if you have to want to revisit this video that Evangeline's making, because there's going to be three different shafts I'm going to show you, and each one of them is going to have different markings for different reasons of what caused it. These are the type of things I like to call, like, refer to them as thumbprints. Again, the design of a lot of these compressors has not changed over the years, quite honestly. So the physics of what happens inside there when refrigerant boils off is the same explosion that happens every time. It's the same thing as an engine motor. It's the same thing. So the reason it's important to understand this is the oil starts in at this end, okay, and works its way back all the way back through here. It's slopping up through the pistons and what have you. So at the beginning, it's going to get a little bit of oil. What oil's there mixed in with that liquid refrigerant, and the further it gets away, the less and less, more refrigerant and less oil. So you're going to have progressive wear. Here's the front, getting worse right here, getting even worse back here. And if you look at the shaft, the same thing holds true. This is a teardown, by the way. This is the same compressor straight across. Bearing, not so bad. Starting to see a little scarring. See the comparison over here? Now it's really getting scarred up. We're getting less and less oil, more refrigerant. It's tougher to get back there. This is an actual to your left over there. Uh, that is a brass bearing. Lost control of my laser pointer. It's floating on me. My bad. Okay. That is actually pressed into the core of the compressor. That bearing there. Okay. That became so hot that it actually seized on the shaft. This is not that uncommon, believe it or not, when things like this go awry. Now, what's really cool now in the next year, we're still in liquid floodback, but this is really important for me to point this out to you. I think to wrap your head around this, if this is the only thing you learned today, you've really hit a home run here, okay? And I'm going to set this up for you. Now remember, I said most problems start mechanically, but I or the technicians see it as electrical. Well, they're with limited information, especially on welded products. They can't tear those open with a can opener out in the field, right? And most people don't take the time to open up the semi-hermetics, even if they can, okay? They just don't, all right? So what do I mean by that? Well, here's a rotor. Look how scarred up that is. This rotor is around the shaft, and then we have the wirings and the windings and stator around that, okay? Where is that at? It's right here in the motor. What's happening? Well, we said that bearing right there that came off in the core right here is going to get sloppy and start to bore that out, start to grind with a little lubrication. What happens when that starts to bore that out larger? The weight of this motor starts to sag. Here's your windings. Here's your rotors. The rotor's rotating. The windings are stationary, right? Okay. What happens then? The rotor sags. It arcs into the windings. This is all from floodback, stator damage. But when you and I or technician goes up to the compressor, up, shorted to ground, shorted out, got electrical issue. Well, there was a bad storm that came through. A technician will do everything it can to convince himself to tell his service manager, here's what I think happened. Maybe the store manager said I had a brownout the other night. Okay, that's probably what happened. They didn't rule out the problem. Now, a seasoned person that's been to courses or just knows will know this, but just letting you all know, this is the reason we talk about that so much. This is a actual compressor that came out of one of our teardowns that a student or students put these pieces together, and we said this is a perfect example. This is a template of what we're talking about. And we see it all the time, by the way. This is just showing you what that looks like on a scroll. It's the same song and dance as we get away from the furthest point of the oil down here. By the way, this green is what we call a lower bearing, and that is supposed to be submerged in oil all the time. Okay, I'm setting up that for you later on, planting a seed. for later on picture that I'm going to show you of the lower bearing. But the scroll set's the farthest distance, and that's what that scroll set looks like. Okay. See how blue that is? See if I can get my camcorder on here. Really, really pushing the envelope here by possibly freezing up. But this is, if you can see this, this is what this is what a good scroll set looks like. I don't know if you can see that or not, but notice how shiny and kind of swirly that looks there. That solvent's gotten in there. Remove that lubrication. That's all we have. We don't use any kind of tipping material on our scroll set. Simply a seal of lubrication, the oil between the two moving parts. This is the fixed scroll, by the way. This is the one that sets on top. So this is actually upside down. This would set down on top of this orbiting scroll, which is orbiting. The fixed scroll is stationary, pretty much so. I mean, it moves vertically 1 millimeter. Okay. This is the bottom of that orbiting scroll. See the little squirrely marks here? All right. It's orbiting. See how oblong this looks like, or out of it's not what I want to call circular, symmetric. It's not perfectly round like it was from the machining at the factory. That's because this unloader bushing in here, which gets heavily lubricated, the shaft's running right inside here, and the oil comes up right up in the bottom of this orbiting scroll at the bottom. Okay. And this is the unloader bushing over here to the right that's all scarred up. You can see the scarring, which has caused friction, obviously. And this is the top of that shaft. The orbiting scroll I just showed you, there's a hole in the bottom of it, and it sits right on the shaft. This is the oil that's coming up through the center of that shaft. There's a little hole you can't see here. This cup fills up, and the oil runs back out and to the bottom of the scroll. Okay, this is a scroll compressor, obviously. Okay. Now, something you may or may not know, not really part of this program, is the only oil pump in any of our scrolls are in the variable speed. All other scrolls do not have any kind of pump in them. Okay, it's all done by using physics, basically, engineered to make the oil come up through this hole. All right. How are we going to prevent refrigerant flood back? What's something we can do? Does anybody want to take a stab at how could we walk up to a system and possibly guess that we have liquid refrigerant flood back? Would anybody know that answer by chance? We would check the superheat. And when we check the superheat going into the suction line entering the compressor, if we can prove even 1 degree or 2 degrees of superheat, we can prove that we don't have liquid floodback. Okay? Because superheat, we should be superheat when we leave the evaporator or the case, right? We leave the evaporator, we're changing liquid to saturation, boiling off. In our evaporator, we're evaporating, right? Into a vapor. By the time it leaves the evaporator, we should have total vapor. And superheated vapor is nothing more than any refrigerant above its boiling point, any vapor above its boiling point. So if water boils at 212, the very second it goes to 213 degrees is that 1 degree above its boiling point. It's a vapor state now. It's the last drop of the pot of water. Okay. You boiled it all off. We're now completely vapor. All right. Causes of liquid refrigerant flood back, a low evaporator load. We lose more compressors. A lot of folks don't know this on low load than we do on high load. And this is the culprit. Okay. When it gets real cool at night, not much load on the evaporator, or for whatever reason, airflow issues, whatever. Also, improper refrigerant charge, overcharged systems. Now, overcharge on a thermostatic expansion valve, TXV, may not cause liquid refrigerant. Why is that? You all know there's a bulb on the backside of the um, evaporator that's communicating by pressure temperature with the metering device on the TXV, opening and closing that TXV, telling, hey, I got too much superheat. Hey, I don't have enough superheat. And it's constantly reading that temperature of that suction line, or it should be. Okay. So when I say it should be, what about a misadjusted or a malfunctioning TXV? You'd be surprised how many times a TXV is not sized properly from the original installation. I hear it all the time from some of my competitors when I sit in conferences that they give. When I'm doing national speaking, I'll take the time to go sit in one of their presentations just to hear, the different our competitors that sell, components like that, Danfoss and what have you. Sudden change in load, hot gas and reverse cycle defrost, heat reclaim, condenser fan cycling on and off, an evaporator fan switch. Maybe somebody forgot to turn the light switch off that controlled the evaporator fan while they were loading up the walk-in cooler. They didn't want that cold air blowing on them, so they turned it off. Thought they were being, wise. I don't want that cold air blowing on me, or the truck driver did it. Turn that off, and then hey, I got to go. Forgets to turn it back on, and so on and so forth. There's a problem, right? Prevent liquid floodback, properly selected components, expansion valve sizing, proper airflow. Air distribution. Again, the person in that walk-in cooler doesn't understand that putting that stock way up and stacking it as high as they can in front of the evaporator, that's an issue. Yeah, you got more inventory in there, and the manager was happy. Your boss was giving you a thumbs up. You didn't understand because if that's not what you do, that's causing an air issue. Okay, that's causing air distribution. All right. Same thing anywhere else. And a lot of folks don't know on our side of things that when these folks do this stuff inside the walk-in cooler, some of the labor they do is maybe some of their job is cutting up cardboard boxes. And on a hot summer day, they'd rather do it in the walk-in cooler than outside by the dumpster, you know? So they'll do that, and the particles from that cardboard box over months of time or years of time will build up on those evaporators. That's a very common problem that we see. Okay. Refrigerant charge, overcharge, sudden, check for sudden changes in the load. Might have to add a suction accumulator to help prevent liquid flood back. Approximate, I want to emphasize approximate superheat setting for general guidelines. Have to be careful when I show this slide. This is not sketched in stone, but just an approximate. Always follow OEM recommendations. For high temp air conditioning, maybe somewhere between 6 and 12 degrees. This is at the evaporator, by the way. Medium temp, maybe somewhere between 5 to 10 degrees. These are nominal. Low temp, looking at somewhere between 2 to 8 degrees possibly. Again, OEM guidelines. Superheat. How do we feel about superheat? Okay. Superheat, again, that's preventing. If we can prove superheat going in the compressor, we can rule out that we have liquid flood back, at least at that minute that we're there. Now, okay. At least while we're there. Now, what it's saying here is the example they're giving is it's 404A. When we go to our PT charts, our pressure gauge says entering the compressor on the suction side at 16 psig. According to this, if you're using 404A on our PT charts, it's telling us our saturated temperature at 16 psig should be minus 20. We're taking our reading actually on the refrigerant line or suction line within 6 inches of that gauge, and we're reading 0. 0 minus negative 20 is a 20-degree difference. Therefore, the moral of the story is we have 20 degrees superheat. We prove that we have superheat. Even though it's 0 degrees at the line set or the suction line entering, we have proven that we have superheat there. Okay. Now, I put this in yesterday because I was doing like a fun fact video for some technicians that I work with that Evangeline mentioned that's out there on my YouTube channel. Okay. The thing I'm pointing out to them is we don't recommend superheat per se. Okay. This is an A bulletin. I highlighted it. Superheat, this same information is in several of our A bulletins. I just chose this one. It's worded exactly the same though. You can find these A bulletins on our AE apps, which is free. You can download our AE app and for free, no commercials, never, you're not going to get hit with a bunch of junk mail. But it states basically that if you have uncontrollable liquid flood back, okay, and we don't dictate superheat or subcooling per se. I get that a lot out in the road. What does Emerson want for subcooling? What do we want for, well, we don't know. That compressor that we make goes out in 5 different applications. It's really the designer that dictates, as you all know, what they want for superheat, leaving the evaporator. Okay. But if you have uncontrollable liquid flood back, we're going to say in a high load condition, we would set that superheat at 20 degrees. And this is after you ruled out, that the refrigerant lines are sized properly. You've got traps where they're supposed to be. You may even have to add a accumulator, possibly. All those things have been taken in place. Set it for high load conditions, and that means the peak of the day, doors open, everything at high load, 20 degrees at minimum. Okay, because at low load conditions, 1 o'clock in the evening, colder temperatures, you may only have 2 degrees, but you'll have something. But what a lot of folks don't know is we have something that we have in our A bulletins that supersedes that. And what supersedes that is another method to determine if liquid refrigerant is returning to the compressor is to accurately measure the temperature difference between the compressor oil crankcase and the sunline. During continuous operation, we recommend that the line difference to be a minimum of 50 degrees Fahrenheit. The crankcase differential temperature requirements supersedes the minimum suction temperature superheat requirements in the last paragraph. To measure oil temperature through the compressor shell, place a thermocouple on the bottom center, not the side, of the compressor shell and insulate from the ambient. During rapid system changes, such as defrost or ice harvest cycles, which is common, as you all know, this temperature difference may drop rapidly for a short period of time. When the crankcase temperature difference falls below the recommended 50 degrees, our recommendation is the duration should not exceed a maximum time period of 2 minutes and should not go lower than 25 degrees difference. Now, I know that's a lot to absorb. I get that, but it's nice to know. The rule of thumb of 20 degrees superheat, at high load conditions, if you have uncontrollable, that's all fine and dandy. The problem with that is that's not sketched in stone for every application. And what do I mean by that? If you have R22 in a system in a low application or a lower application, if you have 20 degrees superheat in some applications with R22 and you set it for 20 degrees, you're going to be smoking that compressor. Your discharge line is going to be really, really high. So it's not one superheat fits all, I guess is what I'm trying to say. So be very careful of that. And Copeland Mobile will tell you what you need on that, by the way. Let's talk about flooded starts. What is flooded starts? Off cycle migration. Okay. My house here in Ohio, it's an upflow gas furnace, fossil fuel in my basement. The evaporator coil sitting on my furnace. We'll just do an easy application like a residential. In January, my fossil fuel gas furnace is heating up that vapor refrigerant in my coil on the top of my furnace. It's traveling through there, right? Hot, heating up. And it's like me, I'm a big guy, I get hot. Now, hot wants to go to cold, right? Second law of thermodynamics, right? The physics of it. Naturally wants to go to a cooler spot. The vapor goes through the refrigerant lines. Let's say the refrigerant line at my house is 15 feet before I penetrate my basement wall. My air conditioner's outside. It's looking for that cool spot. It goes down out to the oil in the compressor. It absorbs in the oil. That vapor refrigerant does. It condenses, rises what the oil should have been to a higher height, and so on and so forth. What's going to dictate how much goes out there and how fast it goes? Well, the delta T difference between the condenser and the evaporator, how short the line set or the refrigerant line is, and how large it is. So if it's a bigger highway, we can get more traffic through there, right? So those are all things we're going to have to take into effect. But that's basically what's happening there. And this can happen in 3 hours or this can happen in 3 months. So a flooded start can happen in a large application in Arizona, going from 100 degrees during the day to like 65 at night or something like that. It's just the difference in the vapor temperature to the condenser oil temperature is how fast it migrates out there. All right. How does a flooded start occur? Refrigerant migration occurs anytime refrigerant and oil are in contact with each other than the compressor and other in each other, and the compressor is not operating. That's key. Off cycle. Liquid refrigerant in the evaporator vaporizes and moves to the crankcase as a vapor. Refrigerant vapor in the crankcase condenses and is absorbed by the oil. All right. This is a refrigerant cooled compressor, which 89% of our compressors are, by the way. The majority of our compressors are refrigerant cooled, which simply means we're running the refrigerant across the motor, we're cooling it, it's coming up through this throat in this design here and going on and coming across the motor, picking up the heat of that and going into the heated compression. But getting back to the flooded start, again, the blue is going to be indicated in our liquid refrigerant coming back. Again, liquid refrigerant is heavier than the oil. So it sits at the bottom. This refrigerant, this compressor is not running. But what's happening is when that vapor is getting in the oil, the liquid refrigerant then is condensing. And this normally open check valve, okay, is letting it fill up on both sides. This normally keeps going through. There's a lower pressure over here, about 2 pounds. We put a vent in there by design. In this design, you can see this vent indicated right here. And when this starts to pump, these pistons start to go up and down. This case would naturally want to pressurize. But by having this vent here and having that refrigerant gas come across the motor and go across that vent, it causes causes a Venturi effect, is what we call it, almost like a tornado. It naturally wants to pull this up, almost like a straw sucking on it, which keeps a constant pound and a half, 2 pound less pressure over here. So again, by our second law, low pressure or high pressure always wants to go to low pressure, right? So that high pressure, it wants to go down that lower pressure there. That oil naturally wants to go down in there. All right. On startup, this pressurizes. We've got more oil in there. On startup, it goes to start, and we have that liquid refrigerant, a burst of refrigerant exploding, boiling off instantly. And the fact that it's over here too, it happens on this side. This check valve that normally opens naturally starts on start, instantly stops, shuts, closes on startup. Okay. So you don't allow this. So we've got liquid refrigerant coming in up here, coming up through the throat that normally handles only vapor. And we've got it exploding down here. So what does that look like? Remember the last one was progressive? This is what we call good, bad, good. The markings are just like a fingerprint again. So this bearing looks good. This middle bearing looks bad. And this looks good. All right. Why is that? Well, again, the design of the compressor hasn't changed all that much. What we find is, backing up here, the liquid refrigerant naturally, by design of this compressor, will naturally come to almost like a peak here and favors this wall when it explodes, blows out, favors this wall. So what we've seen over the years is most of the damage happens right here in the center and less over here. Okay. It favors that wall. So the condensed refrigerant washes out the bearing closest to the divided wall and makes parts break. Again, it's designed for vapor. We have liquid. So it's not designed to take that kind of pressure like a hydraulic pump. Okay. So we start breaking those parts at the bottom. They can also be busted at the top because what's happened, even though it's not air cooled, is we've got this over here because we rose this higher than what it's supposed to be. So we're above this check valve. It doesn't want to go over there anymore. Okay. So it levels out on both sides. When it starts up, it literally goes everywhere. So you'll see broken parts even on the top of a refrigerant cooled compressor. How do we prevent it? Well, the one thing we can do is crankcase. crankcase heaters if you've never heard of them. So factors that affect the rate of refrigerant migration, the length of the compressor off time, yes. Compressor ambient temperature, all right. Temperature difference between the saturated refrigerant in the evaporator and the oil in the compressor. And the refrigerant charge to oil charge ratio, all right. Too much refrigerant. More information on that, go to the AE Bulletins AE22-1182. Again, we have a free app. If you want to look it up, you can just Google it if you like, or go to your app store and just put Emerson in there. Crankcase heaters come in all shapes and sizes. We're making the oil warm, is what we're doing, okay? Is the moral of the story. This is a probe type. This is stuck in some compressors in a dry well. In other words, it's not touching anything. There's a tube that goes on the outside of it. It's not actually in the oil. Okay, getting away from this. This is what I used to see a lot in the years ago. This is the bar type. So this would be the type that's bolted on the bottom of a hermetic, pardon me, at the bottom of this. This is the one that's most common, is a belly band type. Again, all we're doing is trickling low voltage through this. It's kind of like a heating blanket or something you heat your water lines, in the wintertime to prevent from freezing. We're keeping this warmer so that refrigerant, vapor refrigerant, saturated refrigerant doesn't want to migrate out to that cold, compressor oil and condense in there, right? These belly band type will come in different shapes and sizes as far as volts and lengths and what have you. What else can we do? A continuous pump down. If we know that my liquid migration, off cycle migration, pardon me, comes from the evaporator when the compressor's off and migrates and gets down that oil, well, what if we move that refrigerant out of there on shutdown by design? So let's take a look at this. We have a normally opened solenoid valve right here. Okay. System is running. All right. We have a set point. Let's say it's a walk-in cooler and it's a medium temp. Let's just say it's like, 30 degrees in there. Okay. 30 degrees in there. And we hit our 30 degrees. All right. And we hit our 30 degrees and we send voltage back to the solenoid coil to energize it to close the solenoid valve, okay, to shut it off, not allow refrigerant through. Refrigerant keeps moving because the compressor has not shut off. So it goes through our metering device, through our evaporator, past our bulb, our TXV bulb, through our compressor. I'm going to stop right here because this P indicates a low pressure device, okay? And we're going to pretend that the low pressure cutout is set for 10 pounds. All right. It's going to be cut out at 10, cut back in at 20. So there's a 10-pound differential, we'll say. Okay. Again, that's not sketched in stone, and I'm just throwing numbers out to you out there. Okay. But let's just start with that. Compressor's still running. We pump the refrigerant all the way back through our condenser and back to our receiver, which is nothing more than a storage vessel, right? It may be full of a lot of refrigerant in low conditions. In high conditions, there might not be very much there, but it's a storage vessel. That's what a receiver does. So we're going to pump it back here and store it over here. When this compressor pumps this down to so low to where it reads that 10 pounds, it's going to shut the compressor off. Go back to our thermostat, all right, our set point, and we want it set for 30, and it goes to 32 or 31 or whatever. Okay, it de-energizes that solenoid valve. All right, solenoid valve comes open, starts to pressurize the system. The compressor's still not running, by the way. Starts to allow refrigerant to come through. As it senses that pressure rise to that 20 pounds, the compressor kicks on and it starts the whole process back over. What we've done is we've moved the refrigerant over here with no opportunity for this to migrate back to this compressor in the off-cycle migration, okay? This will be the same temperature as the compressor, normally in the same place, right? The condenser and the compressor as one typically, right? Low pressure control setting cutout. This is some information I retrieved from our tech support one day asking a question, and I literally just clipped and pasted the email that I received. I thought it was great information, and it really spells it out for a young technician or a seasoned technician. This is a very common cause of compressor failures, by the way. I was told by tech support when we added to this part of our presentation, they would guess that about one of every 15, 12 calls, somewhere thereabouts, they get a call of, hey, where should we set this cutout at? Or, hey, I think my compressor's damaged and here's what happened. The pump down low pressure control cutout should never be below the lowest pressure shown on the specific compressor's performance chart. Generally, they should be set at 10 to 15 degrees below the evaporator operating temperature. That is good information. If I was a technician, if somebody told me that on day one, that would pay dividends. And a lot of folks don't know that. So I put it on. This was actually part of a presentation, and I made this stuff smaller and added this. This is a performance chart. There is a performance chart for every application of every compressor we make, of every refrigerant, of every temperature. You can find these performance charts on OPI or online product information, and you can find them on Copeland Mobile. But the evaporator temperatures and pressures at the top of the chart. On the sides are your condenser temperature pressures. And I do a series of classes and courses and mini courses on just how to do these. Okay. But lock this away, this 10 or 15 degrees, because quite honestly, I didn't know that. Okay. And this is really hard on a compressor when you pull it down to a zero or, gosh forbid, even a vac. Okay. So be very careful of that. Good information for technicians. Control flooded starts. Locate the compressor in a controlled ambient. Yeah, that's not always as easy as it sounds. You know, a lot of times contractors like myself, even though I bid a lot of jobs back in the day and walked properties with GC, general contractors, and said, okay, here's where we're going to put this, here's where we're going to put that. You really don't have a lot of say so. In some cases, you do. I mean, I've seen places where they'll put their condensers in the warehouse and they actually utilize them for heat in the wintertime, you know, because that compressor runs in the wintertime. You know, that's very common in some applications. Maintain minimum refrigerant charge. It's good information. Maintain adequate oil level. Use crankcase heaters, as we talked about. That's a big one. I'm a big fan of crankcase heaters, and especially with you being north, like we are in Ohio, cold weather. I've seen contractors that use crankcase heaters, and I've witnessed and worked for contractors that do not use crankcase heater, and the difference in their compressor failures are quite extreme. A great difference. And ask anybody that works around that kind of wholesalers or whatever. A lot of compressors fail with no lack of crankcase heaters, and it's not coincidental, by the way. Like in light commercial or residential, I know that's what you don't do. But when a compressor is off for long seasonal, like in cold weather, like we have, it's not coincidental that when folks like myself, consumers, go out and start their air conditioner for the first time in the spring. So this is good information for you personally, or a family member or a neighbor to share with them, that a lot of compressors fail on startup in the spring of the year. Why? Because that oil's still cool, and we just had some freakish high warm day, you know, 82 degrees where it should have been 65, like we get here in Ohio occasionally. And they go to turn that compressor down, and boom, all of a sudden the lights blink and something went out. This is the cause of it. And you just don't get that information back from you. And a lot of times the person that's doing your service doesn't know it because it's a welded product at your home and they don't open it up. But this is the reason for that. Okay. Use a pump down cycle. Now, a pump down cycle you won't see in residential, and you all know that. And also, you may see both of these in an application. There's nothing wrong with that. You may have a pump down cycle with a crankcase heater. That's not that uncommon. Let's talk about slugging. This is going to be a short section. Slugging is quite simple. We're taking liquid refrigerant back to the compressor somehow, some way. It's caught in the suction line, and somehow, some way, for whatever reason, it's coming back. It's going to look differently on different types of compressors. On air-cooled compressors, it's usually a result of liquid floodback. Okay, the system's running. Okay, or it's ran and short cycling and liquid refrigerants in the suction line. It didn't get all, it didn't get out of there on, startup. It comes back. On refrigerant cooled, it's going to be a result of off cycle migration. Okay, so the moral of the story is if you open up a compressor, you'll see a lot of broken pieces. You're taking liquid refrigerant. Notice these are suction reeds, okay, on this discus valve cover plate, okay? And you can see the indentations here. It should be really, really smooth, by the way. It should all look like this. You can see these BB dents like this. This is all stuff that's breaking and causing more damage. This one came completely off. So once these parts start to break, they just cause massive destruction. You can see how these pistons are all, this is from a teardown, by the way, are all pitted up. Okay. I've seen holes sizes my pinky, and I have pretty big hands, right through the piston itself. And I've seen it lots of times. And it doesn't happen all the time, but that's how severe it can get. Wrist pins wear down after discharge damage, after the discharge valve damage are blown, a blown gasket. Okay. That starts to get, liquid starts to get in there and it causes damage. All right. This is a aluminum connecting rod. This is a steel wrist pin. This would be where the piston connects onto to allows it to do that thing it does inside that cylinder wall. And what I mean by that thing it does is do this in the classroom. Here's your connecting rod. This is your wrist pin. The piston would be along there inside the cylinder wall. Okay. So when you walk up to a compressor, if you do any kind of job site visits and you get up to the top of the, whatever, into the rack room or the top of the ladder or whatever, and you hear knock, 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 that's what's knocking. That's what you're hearing knocking. Okay. Kind of like throwing a rod in an engine. You hear that knocking there. That's what you're hearing knocking. And I typically, what I do in the classroom is I'll take a piston, a good piston, and I'll pull on this right here. Again, keep in mind the piston's still on here. I'll pull on this section, this journal that connects on the shaft. I'll pull on that and I'll hang on to the piston. And in a good application, it won't be able to pull apart. In a bad application, I can yank on that piston and it'll clack. It'll go knock, 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 something like that. And it really gives them a good visual or a listening tool. Here we had the piston literally fall completely out. This is inside the cylinder. It's laying in the bottom. We found this one, the bottom. This is really, really common, by the way. Not uncommon to have the crankcase shaft broken in half like this is here. Here it exploded. We got refrigerant here. This is the suction side of the valve plate, by the way. This is the discharge side. These things right here are what we call cantilever backers. They're designed to prevent the stainless steel reed valves that open up from busting. The reed valve, the stainless steel reed valve, is designed to open up by the pressure with ease of opening, but they don't want to open too far, so these back them up. Okay, they're cantilever backers. All right, they're kind of concave at the end. All right, very, very solid. They're bolted down too, by the way. All right, but this gasket blew out right here and allowed that to go over on the other side as it pulled in from the suction side. You can see this should be all, for lack of better words, this should be all shiny. Okay, and it's not. It's obviously burnt black. This got extremely hot. This is a scroll set that actually broke. It knocked the scrolls completely off this orbiting scroll. That's hard to do because a scroll, as you may know or may not know, will tolerate a little bit of liquid. Not a bunch, but it'll tolerate more liquid than a reciprocating compressor by far. This is the Oldham coupling. This is the same teardown, by the way. You can see the compressor sitting off this side. This was a major teardown area that we actually did at the factory. This was multiple compressors that failed at the same time on the same system. So obviously it was a problem. Overheating. Overheating, the number one cause of compressor failures. Reasons for overheating: high compression ratio. Okay. High head pressure, low suction pressure, or the combination of both. High return gas. Okay. The temperature of the gas is too hot going back into the compressor. What might cause that? We'll talk about that. Lack of external cooling. If it's an air-cooled compressor, it's supposed to have 650 CFMs, like our K bodies are supposed to have, and we don't have that. We have a problem. Okay. The hottest point in the compressor in this design, this split head here, this is a divided head. Okay, we got the piston here. This is our suction side. This is our discharge side. So we have cool, low pressure compressor coming in. We have a little gap there. This should actually be filled in with blue. Say we're on the downstroke, gas fills up. These reed valves open and close, high pressure going to low pressure. This piston pushes up, and as this area gets smaller and smaller in this cylinder wall area, what happens is not to deep dive too much into this, but those molecules have a smaller space, and you may already know this. I don't know a lot about your backgrounds, but as the molecules get more in a smaller confined space, it gets warmer. The molecules start to move faster, which causes high heat, and that's where we get the reed valve to open up. And it's a temperature pressure relationship that causes that reed valve to open up. That gate opens up, if you will. Again, even though this is high pressure, or this is high pressure, this becomes higher than that pressure. So again, high pressure follows low pressure. The reason I say that is that's the way I teach, because I never know if somebody in the classroom has 22 years experience or 2 hour, 2 days of experience. And I only have 8 hours with them, and I'm back on the plane teaching somebody else in a different city. So I try to make it as simple as possible and just remember the fundamentals that high pressure follows low pressure, and hot goes to cold. I try to keep it very simple because again, I see this all the time where someone else sees it in a millisecond. So, but it's all following that gas. We're heat movers basically is what we do. We're moving heat. All right. Key facts about oil: we lose our lubricity at 300 degrees and 320, somewhere between 300 and 320. Okay, start to break down and actually carbon up 350. You'll notice, if you don't already know this, when I came to Emerson, what started to pop out in my mind right away by absorbing all this information 4 years ago is in my application engineered bulletins that I started to read even on the weekends, is I noticed that all the protection inside of our compressors hover somewhere around 270 to 290, 260, 290. Whether it's a pressure or a temperature safety device, they all go off around that temperature of somewhere there. And why is that? They're protecting the compressor or the breakdown of the oil to 300 degrees. Okay, and I'll explain to you why that is. This just shows how hot this got. This, what I really want to show you here is, here's these cantilever backers at the bottom of the screen, dead center, and you can see they're made of steel, okay, of actually cast iron, and they're broken off. Remember those being bolted on? The purpose of those was so these reed valves wouldn't break. Look, these reed valves normally don't have this circle on there. That's how hard this was hitting with the piston. Okay, see the markings on here? That's the cantilever backer, by the way. This is the back of the cantilever backer. So this is the top, this is the bottom. So it was laying right on there. This is the teardown. Okay, they actually filmed this in the teardown area here in Rushville, Indiana, over there in our teardown area. This was due to someone sending this back saying they got a bad compressor. So they have to take these pictures and send, no, well, here's what happened. Here's why it happened. This is a discus type. Okay, this should be all, again, for lack of better words, this should be all shiny silver. You see how hot that got. This by just looking at this, even though I don't do this every day, as far as like the teardown people do, that's been here for 42 years, I do it all the time. Every week I tear down compressors pretty much. I can tell you for sure that this got almost as hot as 350 degrees because it started carboning up. And this, by the way, I don't know if it's a piece or the reasoning. I wasn't here at this teardown. This is the screen that the oil goes through at the bottom of that crankcase. So this is all blocked and everything. All right. See how dark this is? The screen's completely, this should be, again, this is stainless steel, shiny silver stainless steel. And if the oil's right, this should still be somewhat shiny stainless steel, right? But it's not. So we start to get wobble inside there because this is the thinnest film of oil and we've got a lot of heat there, okay? Notice what's going on here. Here's our thinnest film of oil in this design, this discus design, and all compressors are like this. I mean, the whatever is causing the compression is the closest to the hottest point of the compressor. Makes sense, right? We're causing because that compression is causing that high heat, right? So we have the hottest point in the compressor right here in this design, the red high discharge gas. We have the thinnest film of oil right here between the piston and the cylinder wall. Okay. High heat is going to cause the viscosity to change on this thinnest film of oil. It's going to get even thinner. When this starts to get hot, it starts to deteriorate, and this piston rubbing up against this cylinder wall causes friction. So instead of going up and down because it's perfectly fitted to do what it happens in operation by design, it will start to get some wobble to it. That's why this arrow is pointing left and right. There's rings on the outside of some of these pistons that have oil rings, and they look like this. And what happens when they start to favor one side is they wear on one side. All right. And they cause like a blow by on that piston, which pressurizes the crankcase. What we have the students do when we lay this out, when they see this, before they go out in the shop, is to break these in half and lay them across from each other. Again, these are supposed to be symmetrical. You can see how much thinner this is compared to this. So it was really wearing on this one side. Again, it starts to get crazy on one side and it'll favor. Where this one's more symmetrical, and typically this will be, it'll really start to wear on the piston closest to the cylinder wall, okay, or the divided wall, pardon me. This is what we call a muffler plate. This is actually on the bottom of the scroll before it, when it leaves this hole, put it this way, it's at the top of the scroll. This is the discharge point. Right below this is our scroll set. In fact, this fixed scroll is what's right below it. This is upside down. Again, see how blue this got? Okay. This should be, again, shiny silver. This is cast iron. So this got really, really hot inside that scroll set. This is what we call the floating seal. This is typically, a silver green gaskets inside here that you can see very, very clearly when it's not damaged like this. So this was, to my guess, is over 320, almost 350 inside here. So how are we going to prevent overheating? What causes overheating? Low suction pressure, high condensing pressure. A normal compression ratio in an air conditioner is 3-to-1. Okay, it's a ratio. All right. The farther those numbers get apart, the higher the compression ratio. This is my head pressure. This is my suction pressure. The farther they get apart, the harder the compressor works. The harder the compressor works, the hotter the compressor works. The hotter the compressor gets, the thinner that film of oil gets. Okay. So it's a disaster. It causes a high compression ratio, which causes high heat. Okay. All right. So high compression ratio is a fancy way of saying high head pressure, low suction pressure, or the combination of both. All right. The lower the temperature, the lower the pressure, the higher the compression ratio by natural. Okay. Okay. So air conditioner might be 3-to-1, medium temperature might be 5-to-1, and low temperature might be 10-to-1. Okay. All right. And I'm not sure if I taught you how to do compression ratio or not. We're really close on time, but I'm going to do it anyways, real quick. I don't remember if I did or not last time. Did I teach you how to calculate compression ratio last time? Anyone?
I don't believe so, Don.
Real quick, condensed version. If you're looking at refrigerant gauges, we're looking at a low side and a high side, suction and head, right? Blue and red on the old analog type, okay? What those gauge pressures are called is PSIG. That's our gauge pressure. We all get that. In order to figure out compression ratio, we have to add our atmospheric pressure to whatever our gauges are. So if we have 185 on the high side and 5 pounds on the low side, we would add standard atmospheric pressure. Standard atmospheric pressure to all of us is say is 14.7. For easy math, we round it up to 15. So we'd take 15 and add it onto our 185 on our high side and 15 onto our 5 on our low side, which would be 20. So now we have 200 over 20. It's a divisional problem. We take our 20 into that 200, we would get 10. Okay. Whatever number we get, we would put it in front of 1, whether it's 7 to 1, 10 to 1, 12 to 1. That's our compression ratio. We need to change PSIG, gauge pressure, into PSIA, absolute. Are you with me on that? And that's how we calculate compression ratio. So by gauging up, a technician can tell a lot about what's going on inside that compressor, even though they can't see inside that compressor, okay? And if it's a high compression ratio, I can almost assure you that you're going to have a high discharge temperature, okay? So a little bit off topic, but I think it's important to understand that. What causes high condensing pressure? Blocked or dirty condenser, recirculation of condenser fan, erratic condenser fan operation, maybe the capacitor's going out, overcharge of refrigerant, non-condensables, undersized condenser. What causes low suction? Wrong size components, metering device misadjusted, loss of refrigerant charge, plug dryers. Oh boy, that's a big one. I could spend an all day doing a class on low suction pressure. It is horrible on a unit. It's the worst. Suction line pressure drop, dirty filter dryers. Okay. Uninsulated suction lines, okay, will cause high heat. Uninsulated, maybe this is in an attic or suction line. Maybe it forgot to get insulated, or maybe somebody had it insulated and when they pulled it through a small hole, it ripped the insulation. Or maybe it's been up there so long it dry rotted. Again, hot wants to go to cold. It absorbs through that suction line. So your superheat might be great leaving the evaporator, but when you go to check your superheat entering the compressor, it's extremely high, which is going to then in turn go into the compressor high, which then in turn is going to have high discharge. And it just goes on and on and on. Okay. You know, if we have a misadjusted TXV that's not allowing enough refrigerant through, okay, liquid refrigerant, our superheat might be starting way too soon in the evaporator. You know, we might be starting our superheat at midpoint where it should be at the tail end of the evaporator. Maybe we're not using our head cooling fans. This, by the way, this particular fan, only because I have seen this stuff so much and read so much on it, is this cooling fan is a 1,000 CFMs, by the way. And this will actually, depending on each application, usually below minus 25, we'll ask to add maybe a refrigerant cooler, which is on the side of this compressor, and a head fan, cooling fan. Okay, but you can find all that in a bulletin, AE4-1135. Critical internal temperature. Anytime anyone's on any job site, they should take a temperature reading 6 inches leaving the compressor on the discharge line. And that temperature should never be above 300 degrees. Okay? Why? Or 225 degrees, pardon me. 225 degrees. And why is the 225 degrees significant? Because at any compressor, we lose somewhere between 50 to 75 degrees heat. So if this is the hottest point inside that compressor at the top of the piston discharge area, and we lose 50 to 75 degrees 6 inches down line, let's assume we lost 75 degrees. We add that to 225, that gives us that magical 300 number, right? And at 300 degrees, we start to lose lubricity. Now, I used to say all compressors. I backed off of that because I only represent one compressor, and that's Emerson or Copeland. But really, it's not even based on compressors. It's based on oil. And that's what I said. All of our safety devices, it's not coincidental, all go off somewhere below 300. The highest I've ever seen is 290. But 260, 290, we never want to get close to that 300. Okay. And that's why on certain applications where we don't have protection inside the compressors, some of the OEMs request, they'll have a temperature reading over here. Now, it may be set higher than 225. It might be 260. The difference is at 225, we let you run. At 260, it shuts you down. They know it's way too hot. Okay. Now, this rule of thumb, if you will will hold true on all semi-hermetrics and about 90 some percent of the scrolls out there. 90 some percent. I just use it for everything. That's the way I was taught. But the small percentage it doesn't apply to have some type of thermocouple or thermostat that's reading that temperature on the discharge line. Okay. That might be shutting off at 260. So what we're saying there on that small fraction of compressors, the 225 is insignificant because they're going to shut you down over here by design. And this needs to be put back on that discharge line. It does not come with the compressor. So it can't be just blowing in the wind. That is the only protection on some OEMs. Let's talk about loss of oil. How do we lose oil? Oil leaving the compressor must equal oil returning the compressor. Loss of oil, this is what that shaft looks like. Even wear pattern on all surfaces. Always like this, by the way. Always like this. Dark in color, nothing jumping out at me where it's more consistent one area than it is the other. Loss of oil, it does not discriminate. It's straight across, does the same scarring, does everything the same. Okay? So why I like pointing this stuff out is on these three different shafts, we've had progressive wear, we've had good, bad, good, we've had even wear patterns. What I really like about that is setting that up in the technician's mind that if they start to get better and start tearing compressors down and take the time, whether it's out in the field or at the wholesaler, say, hey, I'd really like to look at that. I'd like to educate myself. As long as they put the parts back in the compressor so we can do our own analysis, if you will, put them back in there, they get to learn that. It's really like a thumbprint. It really is. Look at this one. Same song and dance. The only difference here is those bearings that are pressed in the core of the compressor seized on there, right? It's seized on there. This is supposed to be perfectly fit in there. That's that unloader bushing around that orbiting scroll again. These are all these little crunchies here. This is the top of that shaft. Remember how shiny and nice it looked? That hole? This is where the oil comes out of there. This is loss of oil. We have no oil up there. We're starting to do damage. This is that lower bearing I showed you at the very beginning of the class. This is submerged in oil all the time. The shaft sits inside internally in this female part of the hole. Okay. See the scarring in there? That should be very well lubricated and obviously is not. Loss of oil. How does it happen? Hey, if you're using an oil safety switch of any kind and it's tripped on oil pressure switch, that's a warning sign of trouble. Don't just click it back on and say, hey, there was a lightning storm yesterday, or, lightning storm just went through and the manager convinced me that was the problem. I'm on my way. Here's your bill. I got another call. You need to look that over. Before oil pressure switch is reset, look at the compressor site class and record the oil level. I made those all caps. Trying to be funny there, but record the oil level. If no oil is visible in the sight glass, that's a problem. If oil level is in the sight glass, that's a bigger problem, in my opinion. What do I mean by that? Okay. On a normal operation, vapor refrigerant comes in here, cools the motor, goes up through the throat, does the Venturi effect, pulls that gas out of that crankcase, allowing this to be about 1.5 pounds, 2 pounds less in pressure, right? That low pressure or that higher pressure gravitates to the low pressure. So that makes it easy access for that oil to come through. This is a normally open check valve. I say normally open because 99.9% of the time it's open. But I think they refer to it as a floating or something like that. But it's normally open, okay, for the sake of this conversation. Normally open. The only time this would close is on a flooded start or on the original start immediately, because there's not enough pressure build up here lower yet from this vac it causes. So it's equal. So this will close for just a split second. This could be a ball check valve or a disc type, but it's normally open. Okay, the moral of the story. So it naturally wants to go through here, the oil, everything, life is good. Oil's being picked up through that tube we talked about, comes down through the shaft, lubricating all the journals. There's holes drilled through that shaft, lubricating all the bearings. Up in here, there's a hole drilled up through the journal that goes to the top of that wrist pin and lubricates here. It slops all around inside the cylinder wall. Life is good. This is what we like to see. Okay. If we have a pressurized crankcase, which means for whatever reason, we walk up to the system and the sight glass is full and we don't know why, but yet the core sense or the Centronic or whatever device we have is set or tripped. And we're thinking, what the heck? Is it a faulty core sense? Is it a faulty core sense? Centronic? Because there's oil in the sight glass down here. It's halfway between what's going on. So we just reset it and go on our way. Well, we need to not rule out a pressurized crankcase. This is a real head scratcher. When this starts to bore out, the piston starts to bore out, and we start to get that ring wear, that slop we talked about earlier. As it starts to bore this out, it starts to get some blow by or pressurize this crankcase. And it becomes so much so that it overtakes the vent. In other words, this is not 1.5 pounds, 2 pounds. It might be equal, or it might be greater than. For whatever reason, this normally open check valve closes during its running. Now watch what happens here. This oil that's normally coming down here through that's wanting to go down here into that lower pressure, now can't get through because the check valve or the gate is closed. But the compressor doesn't know that. So it's still drawing oil from our pickup tube down to our shaft. It's being pumped down through the shaft here. There's a little pump down here. All right. When it gets so low, it doesn't sense oil. It trips whatever mechanism we're using for low oil to go off for safety. Shuts the compressor down. Warning light goes off on whatever we're using. Okay. Whether it's mechanical or electrical or whatever. Okay. Compressor shuts down. This depressurizes. Okay. Right. It stabilizes, causing this to be equal. Once the pressure gets even or lower over here, this will open back up, allow that oil to start coming down and filling the sight glass. I show up and I'm thinking, what the heck? What we need to do in that case to rule this out is there's a plug on the side of our compressors, our semi-hermetics. And you can take that plug out. Okay. It's literally just a plug and put a brass fitting in there. You can permanently keep in there because this is how you would check your oil pressure too, by the way. All right. But you can put brass fitting there. It's a half fitting, male fitting. You screw it into the threads there. On the other end, you'll have a half-inch flared fitting that fits perfectly on your refrigerant hoses. Put one hose here, put one hose here at our service port going in our suction valve. Turn my camcorder on, just give you a little visual here. I don't know how it's going to help. So what we do is we turn the compressor on. In a perfect world, if the compressor is good and we don't have a pressurized crankcase, when we start that compressor, we're going to slowly start to close this suction valve off, our service port. Gradually close it off. And as we close it off more and more and more, what's going to happen is those gauges will go down at the same time at the same pressures. However, if we have blow by right here, the gauge connected to this port is going to start to go down and it's going to peg out right there. It's going to stop. It won't go down all the way like the motor side will on the suction valve. Okay. So if it's a good compressor, it'll go down together at the same pressures. If it's bad, the crankcase side will stop eventually. Okay. And not continue on. We then know we have a suspicion of a pressurized crankcase. What do you do about it? Nothing you can do. You have to replace the compressor. What causes loss of oil? Poor piping, improper traps, inadequate defrost, loss of charge, short cycling. We have a rule here. A lot of folks don't know. Unless it's a rack system, we design our compressors to run. We would like them not to turn on and off more than 6 times a cycle in 1 hour. Okay. We design all of our compressors to last a minimum of 15 years is how they're tested here at the plant. Okay. That's as long as they're inside the envelope. All right. Minimum of 15 years. Okay. We don't like them to run more than 6 times per hour. Unless they're on a rack system, you can't control that, okay? Because you have mechanical oil mechanisms in place. But if you don't have that, you're not getting that oil back to the compressor if you're short cycling too much. Low load conditions will do it. Hey, if you're working with traps and you want to build your own trap, here's what we say. If you're not buying the traps from an OEM or the manufacturer or the wholesaler, we never want this trap from outside to outside to be 4 times larger than the diameter of the refrigerant line. Okay? So whatever size that refrigerant line is, it never can be 4 times larger than the diameter from outside to outside. It will mess with the turbulence of that oil. If it's too wide, it will not work. It's too small, it won't work. All right. We want it to be sized properly. Now, if it's off a little bit smaller, that's fine, but it can't be larger than that. If you have it larger, you will have some issues with the oil return. All right. It's just like risers or anything else. And I'm sure you're familiar with that kind of stuff. We also want you to trap every 20 foot above the P trap at the riser, at the bottom of the riser before the evaporator. Okay. 1.5 inch fall every 10 linear feet. This is what we would like. I've seen specs from other manufacturers that make cases that say we do everything 10 foot, and that's fine. But we're saying we want a minimum of 20 feet trap every 20 feet above the riser, at the riser. Contamination, this one's going to be a quick section, not a lot to talk about here, just some pictures. Contamination, again, this is the fastest growing piece of the pie, though. We need to be aware of it. Leak dye, very common. These all came from teardowns, by the way. Notice the pallet underneath this plate. This is all gunked up. This sludge here might have come from overheat, all right? This is my favorite one of all. Copper plating. Copper plating is caused by moisture in the system, typically by not pulling a good micron down, not doing the proper thing at the time the compressor was installed, of the installation. In other words, we vacuum pump that down to eliminate any non-condensables or any impurities. Okay, we put it in a vac, we let it hold to make sure it's leak free. When you see something like this, you can almost guess something happened, or somebody gauged up with dirty hoses and didn't blow nitrogen through them, and they put contaminants in there, moisture. But copper plating moisture is acidic. It will eat copper off the refrigerant lines, the wirings of the anything it comes into contact with that's copper. It'll eat that off. Hence the name copper plating, and it will plate anything it comes into contact with. Now, the thing about copper plating is if you don't pull a good micron on day one, if I don't do my job, this doesn't show its ugly head sometimes the first day, the first year, the first 5 years. When the same company follows me up, or Evangeline comes out, and the customer, and you tell them that they have a condemned compressor, and the customer will say, they just don't make them like they used to. When in fact, what a lot of technicians, installers don't understand is it happened at day one. Okay. Look at this compressor, for example. Okay. If you know anything about our nomenclatures on our models and our serial numbers, on the serial number, this is the year that it was made. The third letter here, A, stands for the month, January of 2012. This thing failed July 5th of 2012. It was made January of 2012. It failed it was tore down July 5th of 2012. Here's the real kicker. On the bill of materials, it's an 800 bill of materials. Now, you may not know this, but this tells me that this isn't even the original compressor. So are we fixing the problem? Probably not. We're not fixing the problem. And this is very common. And again, I know it sounds like I'm being biased because, I'm part of Emerson or Copeland, but I'm not, because I was guilty of this too. I was a contractor. I am a licensed journeyman. I'm not up here to judge. Okay. I'm just stating what I've learned since I've been here. And believe it or not, this is what I tell technicians. Everybody's proud when they get to be the service guy, or they got a lot of years and they're better than the installers. But in fact, the people that do the installations that are out there doing the grunt work, it all starts with them. I cannot emphasize this enough. I don't care if you're doing residential or commercial or refrigeration or whatever you're doing, you know, the equipment can be made as good as you want it to be. It is the installer. The person that installs the equipment really sets the tone for how that equipment's going to run. And I know you probably all know that already, but it is huge. Okay. But I like to emphasize that to our technicians, especially if they install, because you can see their chest go out a little bit and start to smile and look at the guys across the room that they're at, that are the service guys going, yeah, but it's true. My son is a licensed contractor, by the way, and he primarily installs. He just passed his contractor's license. He was a licensed journeyman. So he takes a lot of pride in his installations. Here's just some more copper plating. Here's some more contaminants and what have you. This is, I was told this was some type of flush, which we don't allow flushes in our compressors of any kind. We would allow them if they were tested, but we put the testing responsibility on the company that has the product. They have to use their money. We'll test it for them, but they have to pay for that testing. We're not trying to say it's bad. It's never been tested, so it has to be tested. The stuff that we do allow has been tested. This is from a teardown again. This is somebody using a hacksaw or a sawzall, not a tubing cutter on copper. These are copper flakes. The only thing we want in our compressors is oil and refrigerant, maybe some nitrogen at times, not while running, but cleaning up. What's it going to do? It's going to cause motor failure. We have a general burn, spot burns, start winding burns, and leads shorted. This would be single phase. This would be three phase, half winding burns, single phase, and primary single phase. Just going to show you some pictures of what that looks like. Again, cause and effect. We see wiring damage. It looks like this when we take our voltmeter, but it actually was caused by something else. This is a general burn, and boy, do these stink. I've done these so many times. I've tore these down so many times, or been around, students or technicians that have tore these down. Seriously, I can almost smell this through this PowerPoint. I mean, that's just how bad these things are. If someone opens one of these up, 3 tables away, I pick it up almost immediately. It's really bad. Here we have a single winding burn on the single phase. Okay. Burnt right in here. Here's a spot wind burning. Again, back to the installation. This could have been hacksaw guy or girl, or sawzall guy or girl. That copper flake got in the system from day one, maybe took a month, maybe took a year, maybe took 2 years to get there, eventually floated through the system and landed right there on the windings and got hot, burnt the coating off the windings and caused a spot burn. You and I, with our voltmeters, saw electrical issue, when in fact it was something on the installation. Contamination, what does that look like? How do we need to clean the contamination up? Well, we can see by filter dryers. These sight glasses show you quite a few things. They can show you a discolorization of the oil. They can show you moisture. This is what it should look like. This is when it's starting to get wet, and this is when it's really wet. We don't want to wait until it gets wet. When it starts to get in the caution area, it may be time to change the liquid line filter dryer, because the liquid line filter dryer removes primarily moisture, some acidic, but primarily moisture. On the suction side, we usually remove our acidic stuff, okay? But on the liquid line, that's when we find most of our moisture, or it condenses better over there, all right? So it's easier to trap moisture on the liquid side, I guess is the best way to put it. These are all different designs, different shapes, different flavors from different ones. The standard from ASHRAE standard of moisture in a system is 100 parts per million. It's acceptable. Anything below that is acceptable. This happens to be our sight glass, I guess, to blow our own horn, and ours reads 50 parts per million. But we don't want to wait until it gets wet. We want it to caution, all right? You can see discolorization. You can see moisture. You used to be able to tell the charge in here if you saw air bubbles. You had flash gas in there, and that wasn't good. Unfortunately, now that with all the blends out there, you can't necessarily go by that all the time. All right. On the suction side, we're going to do a cleanup, system cleanup. All right. Acid removal. This is the suction side. This happens to have where you can take our pressure drop across there. All right. Going back a little bit, Uh, when changing the liquid line filter dryer, whenever the system is opened, every time. That's important. Anytime the system's opened up, we change the liquid line filter dryer. No brainer. That's it. No exceptions. When the pressure or temperature drop becomes excessive, when the sight glass shows excessive moisture. I missed that part of it. That's very important. But so if we get one line of this leaving is frosted up, you can about bet we're using this as some kind of a filter. It's not only a filter now; it's almost a metering device. All right, you see frost on a filter dryer, that's a give me, or on anything there on a liquid line. This is the suction side. All right, we use acidic detection, test it before, after. In this particular product, yellow is bad, red is good. Okay, this type of suction. All right, these aren't leave-in styles. Right. This is the kind of stuff you see in commercial or light commercial and residential. Normally on a refrigeration, you'd see some type of a canister device you can open and close, but this would only stay in no longer than 48 hours. It needs to be checked in between 48 to 72 hours. You never leave this in. Again, suction pressure is huge on a compressor. All right. Compressor operating checkpoints, suction header, suction temperature, suction pressure, discharge temperature, discharge pressure, oil level. This is just a troubleshooting system checklist that was developed shortly after I got here about 2 years ago. And it was made, I'm going to say, sort of by accident in our application engineers, which falls underneath our application engineers as our tech support. And they started jotting things down and saying, okay, I'm going to draw you out a little diagram and I'm going to fax this or email it to you or whatever they did back then when they first started these. And what they learned was if they sent these out to the person they were talking to on the phone, if the person started to fill it out, sometimes, a lot of times, 99% of the times, they figured out their own problem. So they actually made this form out to be permanent. It's very popular in the class. We normally don't hand these out in class, but I bring them with me. I also have a PDF of this on my phone to send to people. Okay. A system troubleshooting. But if you start adding the temperatures and pressures of what you have in your system, 9.9 times out of 10, before you ever get this filled out completely, you figure out your own problem. Okay. And we sell these by the booklet, and either I can send them to you or Evangeline can send these to you. But we actually print these out in our books now of each class. But like I said, I actually take them as a form with me to each class as an extra little tidbit. On the back of that sheet, you'll find these. Okay. A arrow shooting chart. Okay. What if I have high discharge pressure and high suction pressure, but my superheat's low? Oh, by the way, my subcooling's high, but my amps are high. Might be overcharged or undercharged here. Discharge pressure's low, suction pressure's low, but my superheat's high, subcooling's low, amps are low. These are nice little troubleshooting charts. And I keep a PDF of this with me all the time too. Nice to fall back on. Now, if you don't do this for a living, you're not out there in the field. And even if you do this for a living, sometimes it's important to point out to, especially young technicians, this does not hold true in all applications. What I mean by that is most of these will interact with each other, whether you're using a TXV or a piston, which most everything anymore is a TXV or an EEV. The difference in a piston and a EEV or a TXV is simply this. A piston is a hole. A TXV or an EEV is a hole that opens and closes, right? But the reason I say that is in some areas, if you had a chart like this for a piston and a TXV, these arrows might be slightly opposite. There's not a lot of change in, but some incidents there is. Okay. So just keep that in mind. Most everything anymore is a metering device. But if you were to Google these, for example, troubleshooting charts for metering devices, you might see one for TXVs and one for pistons, and one might be universal. But be aware these can be slightly different in some categories depending on the metering device. Okay. Let's talk about any questions. I ran ahead. That is so unusual for me. I cannot believe it. I ran ahead of Angeline. I hope this is being recorded.
Yeah, I'm here. Are you
Well,
there?
the course summary, I am. Course summary is this: common causes of compressor failures include refrigerant floodback. Refrigerant floodback, hopefully you know now, is refrigerant, liquid refrigerant coming back to the compressor, coming back to our vapor pump. We're not boiling off. Flooded start, it's off cycle migration. Vapor or saturated refrigerant going back into our compressor, submerging in the oil and condensing. Slugging is just liquid refrigerant getting in our vapor pump and busting up our parts. Loss of oil, pretty self-explanatory. Debris and contamination, we know what that is. Overheating, again, don't forget high compression ratio, the number one. Now, high compression ratio, when I say that, again, it's just a fancy way of saying, hey, my condenser's dirty, okay, high head pressure, or my filter, if there is one, is dirty. Airflow issues, which causes low suction pressure, okay? So system corrections can prevent these failures from occurring. And that's all I have.
Thanks, Don. Yeah, it's great. Um, that checklist, for lack of better words, can you make sure to provide that to us? We have a version of that in Burn and in text. I don't know. Are you guys still having people fill that out? Do you know? Like our MSA checklist or whatever we
We have
call
a
it.
we have a diagnostic form that we use, but primarily it's just for water, condensation, that kind
That's
of
right.
thing. I think it would be a good
Touch on
tool
that.
for us to, put into act.
Right. Yeah, we could tweak it for our own purposes.
Sure. We will make sure that happens.
And I
Rob?
believe I provided the he had a what'd you call it, Donna? The up and down arrow flow chart, if you will.
Yeah.
I
Yeah.
believe I provided that to you guys as well in the past. Do you have that?
Yeah.
Okay, good.
Rob, quick question for you. Do we use any of the compressors that we use? Are they any of them pressurized crankcase?
No.
Okay. Thank you.
So on that note, I was talking to my manager, Ben, this morning. Shame on me. I need to get in better habit of doing this because I do it in instructor-led courses, but I'm still learning the virtual as best I can. I mean, I've done pretty decent, I think, but it's, there's still a lot to learn. But I thought about this yesterday because a new employee came on in the marketing area and they wanted to have a meeting with me. And, the first thing she said is, well, tell me a little bit about yourself, which, you should do, right? I don't recall you all, and shame on me for not knowing really, what does your day-to-day look like? Do you all do the same thing, or does everybody have a different role? Because we have employee cost classes here, and I might have, 3 engineers in the classroom that work with motors, and 3 engineers that do this, and an accountant and a lawyer and somebody that works in the lab, and it's a hodgepodge of all these people. So I always like to go around the room day one and figure out, okay, what do you do? Oh, you might be able to help us in that section, but what does your world look like?
Yeah, I'll start since I'm not on mute. Yeah, I do new product development engineering. Basically the chief or principal engineer for refrigeration at Structural.
Okay.
I know myself and the rest of the techs, Tom and David, we're answering the phone calls, taking calls, troubleshooting issues, trying to diagnose this issue and compressor issues and any other form of problems with our equipment, and also quoting up parts for replacement.
Oh, cool. Good. Very good. So hopefully some of this really helped you today. Hopefully.
I found it very interesting.
Good. Good deal. Well, I appreciate you telling me that. I was was telling Ben this morning, I said, I don't know if I ever did ask him exactly what each one of them do. I'm so groomed to do that when I'm live. Or in person. I kind of gotten away from that because there's really no faces there, I guess. So I did look into, Evangeline and I'll talk what you do, what the company does as a whole. But anyways, good. I appreciate it.
Yeah, a
And
lot of what we do, Don, is we try to diagnose self-contained fractional horsepower compressor systems.
oh,
So mainly of what we're dealing with is our small systems, individual cases. So the
okay.
big compressors would hook up to our remote units, but typically we're not too deep into those, into the larger systems.
Gotcha. Okay, well that tells me a lot. Okay, very good. Yeah, you wouldn't have a pressurized crankcase then. Okay, very good. Yeah, yeah,
Yep.
exactly. Okay,
So,
yeah.
so yeah, high head pressure is a big one for us, especially dirty condenser coils. And it's surprising how little that's recognized in the field, it seems, from what I see.
Well,
So,
let's talk about that for a second, okay? Because we got a little extra time, if you don't mind. So, just some things that aren't in that presentation that I've learned along the way, especially with universal fan motors, for example. On condensers, you have some kind of a shroud. If you went out and looked at
mhm.
your air conditioner at your house, and that fan blade, first of all, the pitches of that fan blade are sized for that system. You probably know all this already, but I'm just going to walk through it as if you don't. So they're all sized. So if that freezes up on a motor, for example, that you want to replace as a technician. I didn't know this when I first started. You know, a technician might go to United Refrigeration or whoever and just say, "Hey, I need a fan blade." Well, I don't have that exact model, but I got something like this. Well, they have a gauge that they can set the fan blade on the counter and they set it up there to make sure that pitch is correct. But if they don't get that pitch correct, that alters that air moving, just like CFMs if the wrong size motor is. But what's really important to me is in this day and time, about, I was a service manager for 9.5 years, so I was over a lot of technicians in the field, and we were very high volume. What really caused problems for me or us in the industry is when we went to all those universal motors, and it was good for stock. But what happened they would have a shaft on the motor this long and one size fit all, right? You could change the wiring and make it different CFMs. The reason I'm telling you that is if a person doesn't line that fan up, that blade, even if they have the right blade, perfectly right or close to that shroud area, if it's too low down in that condenser, or too high, it alters that airflow across that coil, and that will mess your condenser pressure. That that will cause major, major problems with your head pressure. But just a fun little fact there to think about too. Dirty fan blades, if something got bent even, or equipment setting too close. I worked with a lot of GCs early in my career, and I used to cringe when we would be doing like multi-housing or big commercial jobs, and the general contractor was trying to save money, and they pour me a 20 by 20 foot concrete pad outside the building and say, here's where we want you to put all the condensers out of the rooftop units or whatever, whatever that looked like, whether it was split systems or whatever. And you got to have that airflow, around that condenser, as you probably all know. That's just like in, anything else, like residential, if you're at your own home or your mom's house or whatever, make sure those bushes are cleaned up around your condenser. That is really, really hard on your air conditioner, or whoever's mowing that lawn. Don't let them mow those grass blades. But all that stuff will call cottonwood. Cottonwood trees are just, it's just terrible in that condenser. But those are all little things. And then obviously the things that commonly happen are a capacitor going bad, a capacitor starting to go out, will alter that fan speed. But again, at the end of the day, you just nailed it with the high head pressure. And this falls true for low suction pressure. A lot of times it's airflow, airflow, airflow. No matter what caused it, it's an airflow issue.
Hey, Don, on an off note, so what would cause a residential capacitor to fail?
High heat,
Okay.
very common. Yeah. So
It,
you
but
You were
Go ahead,
breaking
John.
up. Go ahead. You were breaking up there.
Yeah, sorry guys, but off topic here. Our apartment AC outdoor AC unit failed, and the capacitor blew. He didn't tell me what the issue was, but just kind of
Yeah.
curious on what would cause that.
So so for all of you, and I'm glad you brought it up because I like helping people even in the classroom, like I said, like even if it's off topic about your own home or your, whatever, your rental properties or whatever. But a side note here for everybody on the call is that's a very common part that's changed in the summertime. So a lot of people blame it on the quality of what we get now from wherever. They don't make them like they used to, kind of thing. But years ago, a capacitor was as big as almost as like a fourth of a car battery, and it had little resistors in there. So they failed. If you still have like an old GE air conditioner out there, which sometimes it happens, you run into them. If you see the capacitor, the unit's still running, it looks like a small canteen. I mean, it's like 5 pounds. Now they're like aluminum. I don't have one here handy. They're, I hate to use the word cheaply made, but they're not, the quality's not there. But the long story short is if it gets really hot outside. So you see them fail commonly when it gets like 90 degrees or high in the summer, especially if it's been running continuously high heat. And it's not coincidental that you see all these air conditioners failing when it gets really hot outside. The capacitor fails. And that is one of the first things a technician, including myself, will go up, especially if you're 5 calls behind, because quite honestly, it's easy money. Now, a good technician will take the time and look everything over, and hopefully everybody's doing the right thing. But if you go up to a capacitor, okay, on a unit, here's a common one too. I don't want you getting in the systems for you, but let's say a capacitor is like, I don't know if you can see that or not, my drawing, but it's a square. A capacitor is like a can of beer, if you will, okay? What happens when a capacitor blows, again, I keep going back to 99.9% of the time, but it's true. It will actually, there's like a liquid in there. It's almost like a sludge that keeps it cool. It tries to keep it cool there. It's coils wrapped up inside there. It's basically a capacitor holds a charge. It's like a booster for your battery. Okay. It's like a jumper, starts the compressor up. It boosts through there. Okay. But what happens is when they blow or they go bad, they start to oval or get an egg shape on the top of them. So what used to be like a can in your house of vegetables or whatever, now will start to get like a dome on it. And that's a dead giveaway. As soon as they take the door off of it, that's the first thing they look at. I guarantee you, because that's very, very common. A capacitor is one of those parts that's heavily stocked and restocked in the morning on a person's truck in the summertime for residential or light commercial.
So,
Thank you.
yeah, so when we have to replace start components, do you think that that's where the issue is? It got hot or what?
Well, don't get me wrong. It can happen. Anything's possible. I'm just saying it is very common for a capacitor to fail. And along with that, it's very common to have the capacitor fail in higher temperatures. Okay. Now it could happen on a 75-degree day. It's ran its course. A warranty on a capacitor is minimal. I don't even know if they have a year warranty. They're not a 5-year part. Unfortunately, we've come into a world now where capacitors are kind of like a throwaway part, if you will. They're, uh, quite honestly, they're not that expensive. I'm going to be brutally transparent here with you. I've been out of the field now 5 or 6 years. I want to say I was probably, if I bought in the spring buying time when wholesalers run their specials and you stock up with everything, an average capacitor was probably costing me $7. Now, I'm not trying to make you mad because people have to make a living. There's insurance and overhead and all that stuff. They might be charging you 40, $50, or more. I don't know, depending on where you're at. The point I'm trying to say is they're not real expensive parts for even the contractor to buy. You buy them by the dozen, and there's different microfarads and what have you. But anything's possible to make a capacitor go out. But in my world, where what I've seen in the history of my experience is, it's usually it's either ran its course, it's an old capacitor, or it was hot that day. The reason I say that is a capacitor is on a heat pump. A heat pump runs in the wintertime and runs in the summertime. They don't fail in the heat. They don't fail in the wintertime. I've never seen one fail in the wintertime. It's typically always, and I've even seen them explode on like 90-degree days when it's like mid 90s, like here in Ohio or Indiana. If it gets hot for us, not like Florida hot or Arizona hot, but I can guarantee I'd be willing to bet. I've never worked in Arizona, but I teach there a lot. I've never asked them, but I'd be willing to bet if you talk to somebody from Arizona, if you're ever on the phone, ask them if they blow a lot of capacitors. I can almost assure you they're going to say, oh, all the time. It's just like batteries down south. They go out a lot quicker in the cars than they do up north.
Oh,
Will a capacitor fail on a overheated compressor?
I don't believe so. No.
Okay.
Yeah, I don't believe so. Now you have multi-capacitors and you have start capacitors. There's two different types of capacitors depending on what world you're living in. Okay. Um, For example, on your unit at home, your capacitor will be a multi-capacitor, and there's three spades on top of it. One of them is going to say HERM, H-E-R-M. That's your compressor. The other one's going to spell out fan, F-A-N, and the other one's going to be a common. So the HERM or the compressor and the fan both come off the common, and then you have the other spades are going to the compressor and the fan motor. Okay, but really, again, just think of it as a place that's holding a charge. I know you're all a heck of a lot smarter than I am, but really you're holding a charge. It's not like a battery, but it's a booster, if you will. When that contactor pulls in and everything's supposed to start, it just gives it a little oomph. So, for example, one of the common practices in the field is when you undo a capacitor, okay, when you go up to work on a capacitor or work around a capacitor, when you take those wires off, a person like myself has been trained to lay a nut driver or a screwdriver across the two spades to eliminate the charge that's held inside there. Okay, that's very common for an experienced technician to do because if you don't, you can get zapped from it. Okay.
Okay. Thank you.
Mm-hmm. Anything else?
All
I
right.
think
yeah.
I'm good.
We appreciate your time with us.
You're very welcome.
Yep. Very interesting.
We appreciate the engagement and we certainly are open to doing additional training. If you all think that there's more training you'd like on anything, be sure to reach out to us, let us know. And Dawn, you did a tremendous job as usual.
Oh, thank
And
you.
when I will send out the recording of this. And when I do, I'll also put a link in there to Dawn's YouTube channel in case anybody is interested in seeing some of the items that he has there. Like I said, I myself go to it and really like it. So, did anybody have any last questions or comments?
I'm good.
Yep.
Good
Same
deal.
here.
All right. Well, thank you, everyone. I hope everybody has a great day.
All right. Thanks.
Thank
You
you.